If you have a lot of X-ray data, you will get a beautiful tomographic slice. But if your data is limited, the image quality becomes much worse. In this video, I show examples of various methods for dealing with limited tomographic data. In my video series starting with Tomography 101, I explained the filtered back projection and sinograms and such things. This series of videos, starting with Tomography 201, focuses on image reconstruction from limited and sparse data. In such case, filtered back projection may not be the best method. It could be a good idea to switch to a pixel-based model and use an iterative reconstruction method. I will show you some examples. We took a walnut and put it into a tomography device at University of Helsinki. The walnut was rotated inside a cone beam of X-rays. The result is seen here, showing the projection of the walnut from 1200 directions. For reconstruction, we picked only the data in the central row of the detector camera. This leads to a two-dimensional tomographic problem with fan beam geometry. Inserting all 1200 projection images into a fan beam version of the filtered back projection algorithm results in a tomographic slice with fantastic amounts of detail. We can see membranes inside the nut whose thickness is less than 1/10 of a millimeter. However, imagine if we were capable of recording only 20 projection images. I mean, rotating the walnut a full circle around, but taking an image only between a quite big angular step between the images. Such sparse data may be the result of limitation in imaging time, or restriction in X-ray dose, or maybe it's a device that has a fixed number of X-ray sources all shooting at the same time. So then that's the number of projections you get. This is what filtered back projection gives when applied to 20 projection images only. Of course, FBP was not designed for this kind of sparse data, so we shouldn't be too surprised about the bad image quality. But can we do better with some other method perhaps? If we apply pixel-based variational regularization to the same 20 projection images, we get very different results. Here is the result of total variation regularization, Dobeshi 2 wavelet sparsity, total generalized variation regularization, and shearlet sparsity. Depending on the application, one of these methods could be the best one for a certain purpose of an end user. In the rest of this 200 numbered video series, we will see how to build the necessary mathematical models and algorithms for the kind of iterative regularization I just showed you. Now it's a good time to subscribe to my channel and switch on notifications. Stay tuned for more tomographic content.